Good morning, everybody. Sir has forgotten his speakers today, so he could not speak. So I'll speak on behalf of him. So we'll start with the prayer, and then we'll continue with the presentations. Could somebody please confirm if you can hear the sound?
Yeah, we are able to hear.
Okay.
ॐ श्रीगुरुभ्यो नमः हरि ओम् ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्युषावहै ॐ शान्ति शान्ति शान्तिः ॐ असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतं गमय ॐ शान्ति शान्ति शान्तिः सर्वेषां पूर्णं भवतु सर्वेषां मङ्गलं भवतु ॐ शान्ति शान्ति शान्तिः ॐ लोकाः समस्ताः सुखिनो भवन्तु लोकाः समस्ताः सुखिनो भवन्तु लोकाः समस्ताः सुखिनो भवन्तु ॐ शान्ति शान्ति शान्तिः ॐ पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते ॐ शान्ति शान्ति शान्तिः ॐ श्रीगुरुभ्यो नमः हरि ओम्
So we can take a minute and pray to our parents. Okay. So we can now continue with the presentations. So group 12 can start the presentation.
For group 12, Dev, Shruti and myself, I'm presenting.
Okay. You can start, Desh.
Okay.
In case sir has some questions, I'll be
Yeah,
asking.
okay.
You can continue.
So is my screen visible?
Yeah, it's visible.
Okay. So good morning to everyone. I'm from group 12 and I'm going to present on wing design for our strategic bomber, and these are my group members. And these are the specifications that were given, and the specifications that we took from our literature. And from our previous reports, we found that our maximum takeoff weight is 5041 kg, and wing loading is 2872.8 Newton per meter square. So continuing, this is our mission profile, and it's a basic mission profile where so calculation of our wing planform area. We have our maximum takeoff weight. We converted it to newtons, and then using the formula, we found that area wing planform area to be 172.14, and with using our aspect ratio, we found our B to be 31 meters. Airfoil selection for there are two cruise 1 and return cruise. We have two cruise levels. So for the different cruise, we found out our different two-dimensional lift coefficient, and using the above formula. And next, we have a CL range from 0.2034 to 0.2871. We plotted CL versus CD for three different airfoils, all 6-digit airfoils: 64112 and NACA 638210 and NACA 634221. And we found that NACA 64212 has the least drag bucket in the range of CL we want. So we chose NACA 641212, and this is our airfoil. And these are CL versus alpha graphs, CL by CD versus alpha graphs, and CD versus alpha for the airfoil. And we found out leading edge angle using M as 0.84, and we iterated it, and we found out angle at quarter chord to be 27, where it coincides. So, and lambda is 0.43. And CR and CT has been calculated, and mean aerodynamic chord has been found. It is found to be 5.83, 7.73, and 3.35. These are our final wing specifications, and along with it is our Reynolds number. So moving on, we found B by using M to be 0.84, and DCL by D alpha by substituting it in this formula, we found 5.3119, and CL alpha 0 is at minus DCL by D alpha into alpha at 0, I guess. 0. So we found out all the, and we got a CL equation of 5.3119 alpha plus 0.1389. So this is the CL versus alpha, 3D lift versus alpha. And comparing the 3D and the 2D lifts, we have a graph here. The blue line is the 3D and 3D lift, and orange line is the 2D lift. So moving on, this is our 3D tag. We have an F of 1.322 and Q of 1, and S weight of 351.0623. We found our CF to be 0.0027 and CD naught to be 0.0073 using this equation. And our final CD equation was, this is 1 by pi ARE. So we found CD using that equation. And moving on, we've plotted CL versus CD, CL by CD versus alpha, CL versus CD, and CD versus alpha for the equations we got. And this is our final wing design based on the values we got. We got 5.83 and it's almost near everything. Thank you. Questions?
Any questions to Dev Shrutan from the class? Just a second, Dev. Yeah, Dev Shrutan. So, sir has a couple of questions. So, you have done this iterative scheme to find taper ratio, right?
Yeah.
So, you have to give proper reference to this.
Okay, so
That is what sir has asked. So, you have to cite this here and as well as mention this in the references from where you took this formula for this thing.
okay,
Taper, leading edge angle, and taper ratio.
okay, so
Yeah, and another thing is in your 3D lift coefficient curve, 3D lift curve, yeah, CL alpha is 0.
till alpha at 0.
Yeah, so this, how did you calculate?
Actually, it is minus dCl by d alpha into alpha at 0, I guess. The formula for CL at alpha is 0. So we found that and we multiplied it and it was about 7.96.
But is it 7.96 like CL?
Yeah, we got
Yes, sir. Yeah, so they should then probably there is some mistake in conversion from theta in degrees to radians because 7.96 is like too high for CL, alpha is equal to 0.
okay.
And similarly, DCL by D alpha, the
We
slope.
found it in degrees and we've converted it to radians here. So this must be your final value, maybe.
Okay, but okay, here it is fine, but then CL is 7.96 is like too high now. So
Okay,
here you
okay.
just check this if there is any
So
mistake
we've
in unit.
converted this to radians and this is 0.1389.
Okay.
So the
And
value must
also,
be 0.1389 meters. Yeah.
okay, anyway, you just check it again. And
Okay.
DCL by D alpha, what you've got 5.3119, this is true only if alpha is in radians. So you just check the calculation if alpha is in radians here also. You know, CL
Yeah,
alpha.
actually, I forgot to mention it here. This is actually in degrees. Yeah. When I calculate it, wait a minute, like
Yeah. So
7.96
you have
into
to
5 by
reconvert
180.
radians. Ah.
96 into shift 5 divided by 180. Yeah, it's I've converted it to radians here. I forgot to mention it in, that it is in degrees here. So this
Okay.
has been converted to radians here. This is in radians, but we found this in degrees and I've converted it here.
Yeah, Dev. So this must be alpha at CL is equal to 0, I guess, not CL at alpha is equal to 0. So 7.96 must be alpha at CL is equal to 0, and then when you convert it to radians, it would be 0.1389.
Yeah,
Anyway,
yeah,
just check this again, okay?
yeah. Okay.
Yeah. And this question from my side that dCl by d alpha, your 3D lift slope, you're
Yeah,
using 2 pi by this, right? So this 2 pi is actually according to thin airfoil theory, which
yeah.
is yeah, which may not be exactly true in this case. So what you have, I think what you should do is you can take the slope of 2D lift curve. You have plotted CL versus alpha for your airfoil, right? NACA 641, that 6-digit airfoil.
Yeah.
So you take the lift curve slope of that airfoil and that you substitute here instead of 2 pi, because 2 pi is according to the thin airfoil theory.
Okay, okay, okay.
So use that slope here. Okay.
Okay,
And then you
so
can.
I'll try using it. Yeah, okay.
Yes. Okay. So that's all from sir. And any questions from Dev Shrutan? Any questions to Dev Shrutan from the class?
I have a doubt to sir, so can I
Okay,
ask?
you can.
Actually, we are supposed to design stealth aircraft. That was what we were told. Uh, with this, will we be able to change it to like W form? How will we able to do that? Like, I have doubt on that.
You're asking for W form. Okay.
Yeah, it has for the most stealth aircrafts we saw, we have W like the ends, and the fuselage is here.
Okay. Yes. Yeah, so Devshudan sir has answered your question. So this stage we are doing just a simple design. So you don't like this. This simple design is sufficient for the wing. So yeah, there will be W kind of thing for some stealth aircrafts, but like at this point of time, you need not worry. In later point of time, like when we have refined weight estimation, and
Okay,
we'll take care of that. So
okay, okay.
now this is fine.
Just an approximation.
Yeah.
Okay,
Yes.
okay, thank you.
So, no questions to Dev Shrutan, then we can continue. And next group is group number 3, I guess.
Yes, roll number 3.
Okay, you can continue. Start, Aditya.
Presentation visible.
Yeah, it is. Yes, visible.
So, hello everyone. This is Aditya, roll number 3. and I'll be presenting group 3 for presenting the wing design for our aircraft, which is a commercial jetliner. These are our mission specifications, which is maximum of 300 passengers, a range of 10,500 kilometers, and duration must be less than or equal to 10 hours. And from our previous reports, these values have been derived, which is the estimated takeoff weight. So first is airfoil selection. Our CL cruise came out to be about 0.81. So with respect to that, we selected airfoil, which is the plus 598 airfoil, which has a maximum thickness of 1.1% and maximum finger of 4.5%. So these are our polars, which are CL versus CD, CL versus alpha, CL by CD versus alpha, and CD versus alpha. Taper ratio. The taper ratio, the ratio between the tip chord and the root chord, which we got from one of our reference aircrafts, like averaging out all the reference aircrafts, which is we took it to be 0.2 for the design. The sweep angle selection. It is like it's mostly done to like increase its sectional critical Mach number. We found out our leading edge sweep angle from this curve, which is to be like about 30 degrees. And to convert two-dimensional CL to three-dimensional CL, we calculated DCL by D alpha, which is we derive from the formula with using the aspect ratio of 8.5 and a beta value of 0.72. We derived our DCL by D alpha to be about 6.45. And after calculating CL at alpha is equal to 0, we find in the equation for 3D CL, which is 6.45 alpha plus 0.642. And coming to our design, there are a significant number of parameters involved. After calculating from the formulas, we found the wingspan to be around 65.6 meters and the root chord to be 12.74 meters. And found the tip chord to be 2.54 meters and mean aerodynamic chord as 8.68 meters. So our sweep angle at quarter chord of the line is including all values. We got around 32 degrees, 31.8 degrees. Coming to drag estimation, like using the equation, like all the using all the parts as k, which is equal to 0.042, and Roswell's efficiency to be 0.97. Reynolds number came out to be like 1.79 at 3.6. So from the formula, we calculated our CD naught with CD naught and CD as effective values. The final CD came out to be 0.1267. Thank you.
Okay, I'll just wait for sir if he has any questions. Yeah, Aditya. The first thing is, I think Sir has mentioned about some changes in the takeoff weight estimation for your group. So, uh,
Yes, we have already taken all that into account. That is why we are not able to present the 3D CL graphs. We
okay, so have
changed
you
it after.
incorporated these changes here?
Yeah, there haven't been in the maximum takeoff weight. There has been in the climb and cruise takeoff, during the climb and cruise phases, which we have which we are correcting right now, and we'll send it to Sir ASAP as it's available.
Okay, okay. And another thing is your Ostwald sufficiency factor, E, you have taken it as 0.97. So, Sir is asking, where did you get this value from? 0.97. Because,
We actually calculated it from the formula given in Cork. It like instructed to take E dash as 0.98 and calculate the parameters to get refined E.
can you come again?
A refined or Oswald efficiency factor was told to be calculated in the Cork in the middle of documentation.
Oh,
I did.
you said
Yeah.
you're assuming something. What is that?
And actually, it's like it's a ratio of the maximum recommended E dash, which is like 0.98 was given in the book, and then and then a fraction was E. I think it's E dash into 1 minus D by B the whole square, where D is the diameter of fuselage. So
Okay,
that formula I took from Cork and I calculated E to be 0.97.
okay, but 0.97 is okay, fine, no problem with these. Okay, so and then you have to plot your, I mean, you have to show the planform area of the planform of a section of the wing. I think that 3D diagram of the wing and also the 2D planform shape that is missing. Yeah,
Yeah, actually, the last minute we changed the aspect ratio. That's why we couldn't finish it. We'll include it in the report.
okay, okay, fine. And yeah, this question from my side, that your Reynolds number is in 10 per 6, right? 1.8 into 10 per 6. So, like, why did you choose the Epler airfoil? No, Epler airfoil usually it's for like if Reynolds number is less than 10 per 6, right?
Yeah, but actually we needed a high stat for it, which can be operable from 1 million to 2 million Reynolds number. And we found 7 or 8 airfoils which can do that. But in terms of moment, we found Epler 598 to be more efficient. That is why we took Epler.
Okay, okay, okay. Any questions to Aditya from others? Yeah, Kishore has a question. Yes, Kishore.
No, in your 3D lift slope calculation, you got around 6.45, I guess. Okay.
Yes, yeah. Tell me.
6.45, don't you think it is bit higher than 2D, like 2D lift curve slope? Because according to thin airfoil theory, it is roughly it was 6.28, but 3D lift slope you are getting 6.45. It should be lower, right?
Yeah, but that is because our altitude is 40,000 feet and we need a high DCL by D alpha for 3D coefficient of lift. I also anticipated that 6.45 is a bit high, but I reiterated the calculation for 5 or 6 times, but I got 6.45, whatever.
Okay. Thanks.
Yeah,
Okay, so 10 marks for Kishore, and I think the answer is Yeah, so a good observation, Kishore. Aditya, your 3D lift curve slope cannot be greater than 2 pi as mentioned by Kishore. It will be much lesser than that. So, sir has told you to check the calculations again, maybe some mistake in the calculations. So, and also 2 pi here is for the thin airfoil theory. You have to use the curve of 2D lift slope. Okay, you're plotted for your airfoil, CL versus alpha. You take that slope instead of 2 pi here. Okay.
Okay, I'll look into it.
Yeah, and also Epler is not really a good airfoil for this Reynolds number. Like nothing wrong in choosing it, but as sir has suggested, you can choose some other airfoil. You can also get some NACA airfoils for this purpose because Epler is not really tested, and if even if they test it, the Reynolds number what they're going to get is too low for that. So you already have 1.8 into 10 per 6. So I think Epler is not the right
But
choice.
one sec, I have another doubt to ask, sir.
Yeah.
My other airfoils, like we checked many other Naka 6G airfoils and all, but we are not able to touch my CL max. That was why we chose Epler. Is there any method to find airfoil which can touch our CL max?
Okay. Okay, so yeah. So meanwhile, sir answers his question. I think Rajashri had a question. She can ask.
Oh, sorry, that was a mistake. I'm so sorry.
Okay. Okay. Yeah, Aditya. So, answer to your question, you don't worry about CL max right now because CL max it doesn't come through airfoil. You can always increase that through flaps. So that will come in, further part of the design of your high lift devices where you can increase your CL max. So it can be increased through, deploying the flaps. So now you don't worry about CL max. Just take care of that. Your range of CL falls in the drag bucket of your airfoil. So
Okay.
CL max is not a problem now. Okay. So you just
Okay.
yeah, check that again because Epler airfoil
Yeah.
is not the right choice for this. And also your
Okay.
3D lift curve slope. It cannot be
Yeah.
great.
Yeah. Okay. I'll look into it.
Okay.
Yeah.
Any
Thank you,
questions,
everyone.
Aditya? Thanks.
Thank you.
Okay. So if no questions to Aditya, then I think we can stop for for now, and we'll continue with the presentations in the third hour. And thank you to all the presenters, Dev, Shrutan, and Aditya.